Assalamualaikum warahmatullahi wabarakatuh and good day. My name is Alif Aiman bin Abdul Malik and we are group 13. So our group members are Hafiz, Tishalan, Hanisah, Alia and myself. So today we will presenting on the topic of homogeneous differential equation that which is covered in the chapter 3 and 4. And I hope this presentation will help to understand the concept, solution methods, and real life applications of this topic. First, let's understand what a homogeneous differential equation is. So basically, a homogeneous differential equation is a differential equation where a function on the right-hand side is equal to 0. For second-order linear homogeneous differential equation, the general form is usually basically as ay double prime plus by prime plus cy equals to 0, where a, b, and c are constants and y is the unknown function. The main characteristic of this equation is that all terms contain either the function y or its derivative, and there is no independent term present. To solve this type of equation, we first form the characteristic equation, which is ar squared plus br plus c equals to 0. Then we find the roots of this quadratic equation. The nature of these roots determines the form of the solution. Therefore, solving the characteristic equation is the most important step in finding the general solution of second-order homogeneous differential equation. Now we continue to the cases of roots. So there are three types possible cases for the roots of the characteristic equation. So for the case 1, which is distant real roots, when the discriminant is greater than 0, we obtain two different real roots, which is m1 and m2. And the general solution will become as y equals to a e power of m1x plus b e power of m2x. And the second one is the equal real roots. And when the discriminant equals to 0, both roots are the same. So the general solution will become y equals to a plus bx bracket e times by e power of mx. And the third one is the complex roots. So the complex roots will become when the discriminant is less than 0 and the roots are complex. So the general solution will become as y equals to e power of ax bracket a cos beta x plus b sin beta x, where alpha is the real part and beta is the imaginary part of the roots. Now we continue with the application of differential equations. Differential equations have many practical applications in our real life. Basically, in physics, they are used to model motions, vibrations, and electrical circuits. While the second we can find in the engineering. Of course, they help analyze systems such as mechanical structures and control system. And the third one, we can relate it with the economics. So differential equations are used to model growth, investment, and population change. These applications show how important differential equation in understanding and predicting real-world phenomena. So the last part from me, let's look an example. So the example given here is solve the differential equation, which is y double prime minus 4y prime plus 13y equals to 0. So for the first step, we need to form the characteristic equation first, which is we will change the y with r for easy terms, and the equation will become r squared minus by 4r plus 13 equals to 0. And the second step is we can solve this equation by using the quadratic formula. And we can replace and insert the numbers to the equation, to the formula, and we will get the r equals to 2 plus minus 3i. And the third step is we need to identify the case. Since the roots are complex, this is case number 3, which is complex roots is d less than 0, where the alpha equals to 2 and beta equals to 3. And the last step is write the general solutions. So the general solution for case number 3, y equals to a alpha x bracket a cos beta x plus b sin beta x. And after that, the final answer is we will get the y equals to e power of 2x bracket c1 cos 3x plus c2 sin 3x, where the c1 and c2 are arbitrary constant.
Assalamualaikum and hello everyone. My name is Muhammad Hafiz bin Idris. My entry number is AN250164. So today I'm going to talk about the non-homogeneous differential equation. So, what is the difference between the homogeneous and non-homogeneous? Okay, first we talk about the homogeneous. Homogeneous is the right hand side is 0, and the non-homogeneous where there is a forcing function. But in this topic, we are focused on the non-homogeneous equation. The general solution is the sum of the complementary function, which is yc, and the particular function, which is yp. So now I want to talk about the complementary function. Complementary function is obtained by solving the homogeneous equation. We first form the characteristic equation and solve for the root. There is 3 possible cases, which is distinct roots, repeated roots, and complex roots. Each case gives a different form of complementary function. Okay, next is particular function. To find the particular function, we use the method of undeterminate coefficient. We choose a trial solution based on the form of the forcing function, which is fx. For example, polynomial, exponential, or trigonometric function. If the trial solution is already part of the complementary function, we multiply it by x. The next one is variation of parameter. Variation of parameter is another method to find the particular function. We replace the constant in the complementary function with the function u1 and u2. Then we have the Wronskian. Wronskian is used to help compute this function and check independence. Then we integrate to obtain the particular solution.
Hi, my name is Tishalanal Akivenagopal. My metric number is CN25396. Today I want to talk about non-homogeneous and differential equation. This slide shows how non-homogeneous differential equations are used in mechanical engineering. When a system is subjected to external force such as vibration, impact, or periodic loads, the motion can be modeled by the mass spring damper equation. The term Ft represents the external force, making the equation non-homogeneous. This model is commonly applied in vehicle suspension, earthquake resistant structures, machine vibration, and aircraft landing gear system. For Hooke's law, which describes the relationship between a spring's force and its displacement. For the second slide, it shows F spring equals to negative kx, where F is the restoring force, k is the spring constant, which is stiffness, and x is the distance stretch. The negative sign, which means the force always pull in the opposite direction of the stretch. How do we read this? Stiffness. A larger K means a stiffer spring, a smaller K means a softer spring. Next, linear rule. Force and stretch increase together linearly. Double the force, which is 2F, and you double the stretch, which is 2X. Next, we have simple harmonic motion, or SHM. This is a periodic motion where the restoring force directly opposes and scales with displacement. In SHM, there are 4 steps to complete this. First, the governing equation, where m d square x over dt square plus kx is equal to 0. The simplified form will be by dividing mass, which is m gives us d square x over dt square plus k over mx equals to 0. Then the solution. The position over time is expressed as xt, which is in bracket, is equals to c1 cos wt plus c2 sin wt, where w is equals to k over m is the natural angular frequency. The key characteristic of SHM. There are 4 key traits of SHM to remember. First, periodic. The motion repeats itself continuously. Next, max velocity. Speed is highest at the equilibrium position. Third, max acceleration, which is push or pull is strongest at the extreme position. And fourth, energy exchange. Energy constantly slows back and forth between kinetic and potential energy. Then, solving non-homogeneous equation using the method of undetermined coefficient. There are 4 steps in it. First, solve the homogeneous equation. It shows there are steps shown in the image there. Second will be assume a particular solution. Since the forcing function is cos 2t, assume it as xp equals to t, a cos 2t plus b sin 2t. The factor t is introduced because cos t already appears in the homogeneous solution. Third, substitute and determine constant. After differentiation and substitution, a is equals to b, where a is equals to 0, where b equals to 1 over 4. So xp equals to t over 4 sin 2t. And fourth, obtain the complete solution, which is xt equals to c1 cos 2t plus c2 sin 2t plus t over 4 sin 2t. This is the total response of the system. Next is our example question. A mass spring system is governed by x double prime plus 9x is equals to 6 cos 3t. Use the method of undetermined coefficient to determine the displacement xt. There are 4 steps in it, and the first step will begin by solve the homogeneous equation. The given characteristic equation is x double prime plus 9x is equals to 0, where r2 and r2 plus 9 is equals to 0, which is r equals to plus minus 3i. Therefore, xh equals to c1 cos 3t plus c2 sin 3t. Next, step 2. Assume the particular solution. Because cos 3t appears in the homogeneous solution, it will become xp equals to 3 a to t a cos 3t plus b sin 3t. Next, substitute into the differential. After substitution, a will equals to 0 and b equals to 1, which xp equals to t sin 3t. And the last step, write the complete solution where xt equals to c1 cos 3t plus c2 sin 3t plus t sin 3t, and the interpretation will be t sin 3t.
Hi everyone, my name is Nurhanisa Zulkifli. My metric number is TN250071. Now let's move on to the next chapter, which is chapter 4, Laplace transform. Laplace transform change a function of t into a new function of s. The variable t is transformed into a new variable of s, and the value s must ensure the integral converges, which has a finite value. This allows differential equation to be solved as a simple algebraic equation. As you can see in the slide, the general formula of the Laplace transform is shown, where ft is the original function and the fs the transform function. Now let's take a look at the table of Laplace transform. Let's see how the Laplace transform converts a function of t into a function of s. In this example, the function is exponential negative at. First, we substitute the function into the general Laplace formula. Then, we simplify the exponential terms and evaluate the integral from 0 to infinity. Finally, we obtain the answer, which is Laplace exponential negative at is equal to 1 over s plus a. This result is also listed in the Laplace transform table. Next, we will discuss the 3 important properties of the Laplace transform. In the first one is linearity. In the linearity, we need to separate the function, then we factor out the constant. To solve question involving linearity, the first step is separate the function, the second step is factor out constant, the third step is use the Laplace table, and the final step is simplify the final answer. Next, the second property of the Laplace transform is the first shift theorem. This property is applied when the exponential multiply with another function of t. For example, Laplace exponential t cos 2t, and another example is exponential negative 2t sin 2t. To solve question involving the first shift theorem, the first step is identify the value of a. The second step is find fs from the Laplace table. The final step is replace s with the s minus a. The third property is multiplying by t, and this property is applied when a function multiplied by tn. For example, Laplace t cos 2t. Another example is t exponential 2t. The formula is negative 1 power of n differentiate fs. When we do the differentiate in the calculation, we need to refer power rule or quotient rule. If power rule, the top of function is constant, while the quotient rule, the top of function is s. The step to solve this property is, the first step is identify the value of n. The second step is find fs using the Laplace table. The second step is differentiate fs with respect to s. And the final step is substitute the value of n into the formula. Before proceeding to the inverse Laplace transform, we should understand a special function known as unit step function, also called the Heaviside function. The unit step function acts like an on and off switch. T is greater than or equal to 0 and less than a is 0. T is greater or equal to a is 1. Before time a, the function is off and has a value of 0. At and after time a, the function turns on and has value of 1. Example, ft is equal to 3t minus 3t ht minus 4 when t is greater than or equal to 0 and less than 4, therefore ft becomes 3t. When t is greater or equal to 4, therefore ft becomes 0. Lastly, now let's see how Laplace transform can be used to solve initial value problem. In this example, we are given a second-order differential equation together with its initial condition y0 is equal to 2 and y prime 0 is equal to 3. First, we apply Laplace transform. Then, we change yt into ys using formula in the table. After simplifying the equation, we solve for ys, which is factorize the ys. Next, we apply the inverse, and the last step is obtain the yt.
Hello everyone, I am Nur Alia Zaira, and today I am going to walk you through my section of the presentation where we will cover the inverse Laplace transform, its standard pairs, core properties like linearity, the first shift theorem, and look at some step-by-step examples. Let us get started. So for the next slide, what is the inverse Laplace transform? Up until now, we have been focusing on moving from a time function to a frequency function. Now we are looking at the inverse problem. The inverse Laplace transform is simply the process of reverting a frequency domain function back into its original time domain function. So mathematically, we write this as capital L inverse of capital F of S equals lowercase f of t. So it is very important to remember that the -1 symbol used here represents functional operation. It means, quote, find the inverse of, end quote. It absolutely not an algebraic exponent, which means capital L inverse is not equal to 1 over capital L. So, to solve these inverse problems, we rarely have to calculate anything from scratch. Instead, we match our expressions to a standard reference table. Let us look at the 5 most essential pairs you need to know. So right now, let us discuss the properties that make finding the inverse much easier. The first is the linearity property. Linearity tells us that if we have a long complex fraction with term added or subtracted, we can split them up and find the inverse of each part individually. We can also pull constant numbers out to the front. The rule states that the capital L inverse of the quantity A times capital H of S plus B times capital G of S is equal to A times the capital L inverse of capital H of S plus B times the capital L inverse of capital G of S. So when you see a problem, your strategy is simple. First is we separate the terms. Next, we factor out the constant. And lastly, look up the remaining pieces in your table. Let us apply linearity to a practical example. We want to find the capital L inverse of the expression 5 over the quantity S minus 3 minus 2S over the quantity S square plus 16. First, we separate the terms and move the constant to the front. This gives us 5 times the capital L inverse of 1 over S minus 3 minus 2 times the capital L inverse of S over the quantity S square plus 4 square. Next, we match these components to our reference table. 1 over S minus 3 become e to the power of 3t, and S over S square plus 4 square becomes the cosine of 4t. So, putting it all together, our final answer is lowercase f of t equals 5 times e to the power of 3t minus 2 times the cosine t of 4t. The second property is the first shift theorem. Sometimes the s variable in the denominator is shifted, appearing as s minus a instead of just a plain s. This frequency shift means that the original time function was multiplied by an exponential term. So, the formula is written as capital L inverse of capital F of the quantity s minus a equals e to the power of at times lowercase f of t. So, to solve a shift problem, follow 3 steps. First, identify the shift value a. Second, temporarily hide that shift to find the base function. And third, find the inverse of that base function and multiply your final answer by e to the power of at. Now, let us look at an example involving a shift. We want to find the L inverse of 1 over the quantity s minus 4 square. Our first step is to identify the shift. In the denominator, we see s minus 4, which tells us our shift value a equals 4. Step 2 is to find the base function. If we temporarily ignore the minus 4 shift, our basic function is 1 over s square. So, looking at our table, the inverse of 1 over s square is simply t. Step 3 is to bring the shift back in by multiplying our result by the exponential term. This gives us our final answer is f of t equals t times e to the power of 4t. Okay, that's all.